It's my honor to kick off the NERSC at 50 seminar series in celebration of NERSC 50th anniversary. In this talk, I'll focus on what the title indicates, and that is a description of what we have learned about the universe from low-energy neutrino and neutrino physics experiments, and NERSC's role in the discoveries in several groundbreaking results in neutrino physics in the last quarter century. The first question I want to address is, what are the neutrinos? Well, back in 1930, the neutrinos were postulated to exist by Wolfgang Pauli, an Austrian, and it was finally experimentally discovered in 1956. That is, it took 26 years to prove the neutrinos actually exist. And there are three types of neutrinos, or we call them flavors, that interact rarely with matter. And so as an example, there are around 60 billion neutrinos going through your thumbnail every second, and you hardly notice anything. And these flavors are grouped into the heavier charged leptons in the same family. So for example, the electrons is paired with the electron type neutrino. Muon, as we see in the cosmic rays, is paired with the muon type neutrino, and tau is paired with the tau type neutrino. And there are many different sources of neutrinos. And some examples is quoted here, including Rayleigh neutrino from the Big Bang, supernova neutrino from supernova explosion, solar neutrinos from the fusion process in the stars, especially in our sun. There are also neutrinos coming from the Earth, from bottom up, underneath our feet. Those are from radioactive decays in our Earth's core. And there are also reactor neutrinos from the fission process in reactors. And we also make neutrinos ourselves from accelerator. And so, for example, there are these pictures showing the different sources of neutrinos, including neutrino focusing horn at Fermi Lab, which focus neutrinos into a beam. And since the neutrinos discovery at Savannah River reactor plant by Fred Reines and Claude Cowan, there have been many scientists intrigued by how elusive the neutrinos are. And Ray Davis was one of the earlier scientists who won the Nobel Prize in 2002, I believe, was certainly one of these scientists. He also wanted to understand our sun, and prove that fusion is responsible for power generation in the sun, as Hans Bethe has proposed in the late 1930s. I believe it's 1939 that Hans Bethe proposed that neutrinos, this PP chain process in the sun, produce energy in the sun. And this groundbreaking experiment from Ray Davis back in the 1960s was very difficult. Basically, he had a tank of dry cleaning fluid located down in a mine in South Dakota. It has 615 tons of this dry cleaning fluid. And the reason why he used dry cleaning fluid is because it contains a lot of chlorine-37 nuclei. And when solar neutrinos interact with these chlorine-37 nucleus, they turn into argon-37. So every month or so, Ray Davis would flush this whole tank, 615 tons of dry cleaning fluid, and flush it once a month and collect only a few argon-37 atoms in what we call a proportional counter, and then count the decays from argon back to chlorine. And he has done that for over 3 decades. And over this long 30 or so years, he consistently saw about a third of solar neutrinos predicted by the standard solar model. And I will explain what the standard solar model is. And these are the computing model numerical model of the sun, taking into account all the physics that go inside the sun, like hydrodynamics and the nuclear physics inside the core of the sun. And so, but other experiments have confirmed what radiators saw, and they all saw roughly a third to a half of the neutrinos that were predicted by these solar models. And in 1984, Herb Chan of UC Irvine proposed using deuterium or heavy water to investigate the solar neutrino problem due to heavy water's unique properties for neutrino detection. His team identified a mine in the Canadian Shield as an ideal location because of the overburden, how deep the mine was. And more importantly, Canada had a surplus stock of heavy water from its CANDU reactor, heavy water reactor program. And the construction of SNOW at Kraton Mine in Sudbury started in 1990 when this cavity of the height of about a 10-story tall building was excavated. And after the excavation, this cavity was turned into a clean room. We have to run this detector in a clean room because a teaspoon of the mine dust will ruin the whole experiment. That's how sensitive this equipment is and how difficult to detect solar neutrinos. So since this cavity is more than a mile underground and it's only accessible and was only accessible only by a cage, it's an elevator, but we call it a cage. All the equipment and construction materials had to go through this cage for constructing this detector. And LBL was responsible for the design and the construction of this geodesic structure shown here that will hold around 10,000 light sensors, which are called the photomultiplier tubes. Each of these dots at the back of this sphere is the back of the light sensor. So what's so unique about heavy water? Well, we use a kiloton of heavy water. That's 1,000 tons of heavy water. And what's so unique about that is because heavy water can detect neutrinos in several ways. One way is only sensitive to electron type neutrinos. We think the sun only produces electron type neutrinos. And there's a second channel, detection channel, which detects neutrinos of all active types, the mu types and the tau types as well. Those are the ones that are associated with the muons and the tau particles, as I mentioned earlier. And what is the deuterium? The deuterium is essentially a hydrogen, but instead of just one proton, it has a proton and a neutron in the nucleus. There's another isotope that I'll come back to later, and that is the tritium with a proton and 2 neutrons. So these are all isotopes of hydrogen. So SNOW detected only 1/3 of the electron type neutrino, while what SNOW saw was about a third of the signal came from the electron type neutrino, just like the other experiments before SNOW. It was also detecting neutrinos because it was also detecting neutrinos of other flavor. In fact, two-thirds of the neutrinos detected by SNOW were flavors of different types other than electron type. So if you add up the 1/3 electron type neutrinos and 2/3 mu and tau type neutrinos, you basically confirm all the neutrinos predicted by the standard solar model are there. The only problem is some of these electron types of neutrinos, when they were produced in the center of the sun, turned into a mu type and a tau type while they were traveling from the sun to the earth. And that's also explained why the other experiments never saw, they only saw 1/3 of the signal, because they were all turned into something else that they were not sensitive to. And the only reason, and this proves that if we see this, what we call flavor transformation, it proves that neutrinos have mass, because the massless neutrinos will not be able to turn from one flavor to another. And a massive neutrino is not described in the standard model of particle physics. So this is why this discovery is such big news in the scientific community. And NERSC helped enable SNO to solve this solar neutrino problem. It provided computing resources for data processing and production, and that involves reconstructing the event that we have taken from the detector, event by event, and it also provide the computational power for analyzing the calibration from the energy calibration data. And we also use NERSC extensively to simulate our background, even though we can only tolerate no more than 1 teaspoonful of mine dust, but we spend a lot of time simulating what these backgrounds would look like, and we try to identify them and measure them in our experiment. And on the figures here are 2 examples. One is the solar neutrino event. So you can see that in this case, you just need to fit a rain that come from the solar neutrino interaction with the heavy water. And the bottom one is cosmic muon event. So these are very high energy event that goes through our detector. They're only about 3 an hour that goes through our detector. But these signals have a lot of charge deposited on our photosensor. And it takes a long time to reconstruct one of these events. And finally, NERSC provided us with data storage and archiving ability. The SNO data and codes have been archived at HPSS since 2009. And by the late 1990s to early 2000s, SNO ran a lot of jobs on NERSC PDSF cluster. That's the Parallel Distributed System Facility, which had hundreds of Linux nodes. SNO was a beneficiary of this cluster and had over 15,000 CPU days in 2001. That's shown on the left figure. And that was the year that SNO published its first paper on the flux of electron-type neutrinos from the sun, and the year before the publication of the flux of other neutrino flavors with a lot of analysis activities. These 2 papers form the basis of the Nobel Prize for the SNO director Art McDonald in 2015. And the figure on the right, I think NERSC should be very proud of this figure. That's the CPU time or fraction of CPU used by the different experiments on PDSF. If you look at this figure, SNO discovered neutrino flavor transformation, and KamLAND will prove that this transformation is due to a quantum mechanical effect called neutrino oscillation. And then CDF discovered the top quark at Fermi Lab. And STAR provide evidence for this 4th state of matter called quark gluon plasma. And then Diabase, later on, that is not shown in this graph, we'll find out the value of one of the neutrino oscillation parameter with reactor neutrinos. So a lot of physics results came from the experiments listed on this plot, and NERSC has provided support for all these experiments. Let's go back to the story of neutrinos, and in particular, the neutrino flavor transformation that SNO discovered. KamLAND was one of the experiments that the neutrino program in NSD and the physics division participated in the late 1990s and the early 2000s. What Snow discovered was direct evidence for neutrino flavor transformation from one flavor to another. But what is not known is what caused this transformation. And KamLAND was built to also investigate this particular question. Here, KamLAND detected neutrinos from power reactors in Japan, each located at a different distance from the detector. And if neutrino oscillations depend on the distance between the source of the neutrinos and the detector, and also the energy of the neutrinos. So by detecting the reactor neutrinos from reactors in Japan, we can try to see if we find any evidence for neutrino oscillation because of this detector distance and the energy dependence. What is shown on the map here, the red points are the reactors, and the arrow here shows the location of the KamLAND detector. What KamLAND discovered was very exciting. The vertical axis on the left figure here shows the ratio of the number of detected neutrinos and the expected number of detected neutrinos in the no oscillation scenario. So the ratio is the observation versus theory. So what's shown here is up to about 1 kilometer or so. This is the distance between the source of source of neutrinos or the location of the reactor and the KamLAND and the detector that detects neutrinos. So all these previous experiments show that they didn't see any change in the number of the predicted number of neutrinos. But if you look at KamLAND, which is this red point here on the figure, you see that it only saw around 60%. In fact, it was just slightly above 60%. That was predicted from the no oscillation scenario. And the average distance from these reactors in Japan to KamLAND was around 180 kilometers. That's about here on the x-axis. The dotted line is the prediction of what KamLAND should see if we take the Snow results and the oscillation parameters that we extract from the Snow results. So this dotted line is the prediction of what KamLAND should see. And KamLAND, when they make the measurement, they found it right where the flux should be if neutrino oscillation is responsible for the flavor transformation that was seen in Snow. And more importantly, in the later paper, KamLAND saw a distortion in the energy spectrum of the positron coming out from the reactor anti-neutrino interaction that's shown here on the top right figure. And then the telltale sign of neutrino oscillation is shown on the bottom figure when you plot the ratio of the observed neutrino spectrum and the L/E ratio. That's the distance divided by the energy of the electron of the neutrino. That you see an oscillation type of signal in this plot. So this is the telltale sign that neutrinos oscillate. And that's not it for what KamLAND had done. KamLAND could also detect geo-neutrinos from the Earth's core. Geo-neutrinos are neutrinos coming from the core, from the mantle and the crust of the Earth. And here, these neutrinos came from the decay of the natural uranium-238 and thorium-232 chain in the crust and in the mantle of the Earth. And on the bottom right shows the figure of what the neutrino energy spectrum should look like. And the red one represents what you should see in terms of the neutrino energy for the uranium series, and the green is for the thorium series. And so in that measurement, KamLAND measure what the what the radiogenic heat of the Earth should be from these radioactive decay, and it was found to be around 16 terawatt. And in more recent papers, KamLAND have been trying to untangle the different types of Earth's model, and by using reactor antineutrinos as a probe. And since Snow and KamLAND, we have been trying to find out more on the intrinsic characteristics of the neutrinos with NERSC support. The two main questions we're exploring at LPL's nuclear science division are: how heavy are the neutrinos, and are neutrinos their own antiparticles? The answer to these questions will have profound implications to our understanding of the universe and the standard model of elementary particles. So, for example, if we know that neutrinos are the most abundant massive particles in the universe. So even if they have a tiny mass, they can affect the evolution of all the stellar objects, astronomical objects in the universe. And the second question of whether neutrinos are their own antiparticles, we know that there must be some imbalance between matter and antimatter early on in the universe. Otherwise, we won't be all made up of matter at this point. And so the question of whether neutrinos are their own antiparticles will allow us to see if an imbalance in the lepton number early on in the universe will create this imbalance between matter and antimatter nowadays. And I'll explain that a little bit later. So on the first question on how heavy are the neutrinos, one thing we're doing in the nuclear science division is to measure the energy spectrum from the electrons emitted in the beta decay of tritium. We saw what a tritium is before. It's a proton and two neutrons. When it decays, it turns into a helium-3 nucleus with an antineutrino and an electrons. So by measuring, the Italian physicist Enrico Fermi proposed to measure the energy spectrum near the endpoint of this decay. And you can see in the upper right figure, if the neutrino mass is not zero, there's a small distortion from the case when the neutrino mass is zero. The only problem is only 2 × 10⁻13 of the electrons, of the decay electrons, will appear in the last electron volt of this decay. So there are not a lot of electrons that we can measure. So in Germany, we have constructed this KATRIN experiment to make a sensitive measurement of the spectrum near the endpoint, the energy decay endpoint. And this has been a very difficult experiment, and it has taken a long time. The letter of intent was written in 2001, and we didn't get the first result until a few years ago in 2019. And right now, this experiment has the best limit of the neutrino mass. You can see on the right-hand side, the left-hand plot here, and here what is shown is the mass square. It's not the mass; it's the mass square, which was what we measured in this experiment. And you can see right now the error bar is very small, and the limit right now, the upper limit for the neutrino mass from this direct measurement is 0.8 electron volt over c squared. And in this experiment, because we don't rely on any model, we don't depend on, for example, unlike cosmological experiments, observations, we don't assume a certain evolution model to come up with the mass of the neutrinos. It's just a direct kinematic measurement, just like trying to measure the the momentum of a billiard ball in a pool game. And in this experiment, NERSC has provided a lot of computing support for one of the latest analysis. So, for example, LBL has led the Bayesian analysis for measuring the endpoint near the endpoint of the tritium beta spectrum. And what's shown, so let me play this video a little bit. On the graph here, on the figure here, the red is what we put in as the prior for the Bayesian analysis on the neutrino mass square. And as we get more and more data as we include more and more data in the analysis, you can see the posterior distribution of the neutrino mass square that's getting sharper and sharper, meaning that the uncertainty is getting smaller and smaller. And that's what we included in the analysis when we published the upper limit of the neutrino mass. It is a very difficult experiment. If you look at this map of Germany, we made the spectrometer, this big tank, near Munich, which is the middle of in the middle of this map. But the autobahn in Germany is not, the overpass on the autobahn in Germany was not tall enough for us to move any object of this size underneath it. So what we had to do is instead of driving about 200 miles away from Munich, we had to transport this tank across the waterway in Europe. And here, the red curve, you can see how we transported the tank from near Munich to 200 miles away in where the experiment is in Karlsruhe. And it went through the Black Sea and the Mediterranean before it finally get back to the River Rhine, so we can transport it along the riverway. And the last figure is on the cover of PRL, and this figure is a picture taken when the tank was traveling the last few kilometers from the local pier to the research center. And finally, the question of whether neutrinos are their own antiparticle. Our division is also looking. We have several experiments that are looking into this particular question, and here I've listed a few of them that get support from NERSC in the investigation. So for the first one is the MAJORANA demonstrator, which we just finished at the SURF underground facility in South Dakota. And then we have two operating experiments. One is the CUORE experiment in Italy, and the other one is the Legend 200 experiment at the same lab in Italy. And finally, we're planning two bigger experiments. One is the Cupid experiment, and the other one is the Legend 1000 experiment. Both of these will be in Italy. And these experiments have different technologies, and I've listed the different detector technologies at the bottom in the footnote. And let me talk about the physics, the science of these neutrinoless double beta decay. And certain isotopes, as shown in the upper figure here, can undergo what we call double beta decay, and that's the one on the left. This process is allowed in the standard model and has been observed to have very long lifetimes in several isotopes. But there is also another decay mode that's forbidden in the standard model. That's the one shown on the right. It's called the neutrinoless mode. You can see that there is no neutrino emitted in this decay. It only has 2 electrons. If you measure the energy of these 2 electrons, which is a tiny peak at the end of this typical standard physics decay, which is very broad and a much stronger signal than this neutrinoless mode. because the half-life for this neutrinoless mode is at least 10 to 26 years. And and this is many, many orders of magnitude longer than the age of the universe. And to see one of these signals is very difficult. And these are some of the technical challenges to see this tiny signal at the end of this spectrum. And one of the hardest part is to build an experiment that has a clean enough detector that it's radioactive, the radioactive elements in the construction material and the detector itself doesn't swamp or fake the signal that you're trying to detect. Those are the counts at the tiny little peak at the end. And what we want is about 0.1 count of backgrounds per ton of germanium in case of Legend 200 or Legend 1000 per year in that peak. And how small is 0.1 count? So this is on the left is a typical electronics board, and you see a lot of black dots on that board, and those items are what we call surface mount resistor. And one piece of that will kill our experiment, because each one will give us a signal of about 1 microbecquerel. And 1 microbecquerel is already giving us 0.1 decay per day. So approximately. So one piece like this will kill our experiment. And we want to build an experiment without any material that gives us a signal that's bigger than this. And in terms of NERSC support for MAJORANA and the Legend experiment, at least in MAJORANA, we have adopted NERSC as the official computing platform for our analysis and simulation. And we have been doing near-time data quality monitoring, and NERSC has provided us with a special support so that we can analyze the data with these near-time data with a real-time queue for processing. And we're also archiving the data at HPSS along with a lot of Monte Carlo study. And we plan to continue with this process in Legend. That's happening in Italy right now. And on top of that, we're using more capability from NERSC, such as the GPU farm, to do deep learning on distinguishing between signal and background. And CUORE and CUPID also use NERSC extensively. So in the most recent publication or data release of their 2 10-year exposure, which means they have the equivalent of 2 tons of detector material and counted for 1 year. In that data release, they use NERSC to process the data to denoise the signal that is detected by the detector. And a lot of these analysis takes a long time to do, and it requires a lot of computing power. And also, the most recent publication to test whether the idea of CUPID, which is the next generation experiment after CUORE, also use NERSC for the analysis, and the CUPID collaboration is also using NERSC for design study, design simulation for the experiment. And I've been talking about.
Sorry, can you say how many slides you've got left?
I have 2 more.
2 more? Okay. All right. Thanks.
I'm near the end of the talk.
Great.
And so this is hot off the press. So besides neutrinoless double beta decay, NERSC is also supporting other analysis that the MAJORANA demonstrator has been doing. So this one was just published in Nature Physics online late last week. And I believe NERSC is writing a story on this paper. And this is the summary of my talk. So NERSC has provided a lot of expertise and state-of-the-art computing resources to neutrino research. And it has been instrumental in solving several neutrino mysteries in the last couple decades. NERSC has supported solar and reactor neutrino oscillations and is now supporting researchers in investigating outer neutrinos properties, such as the mass and mass generation mechanism that I mentioned earlier in this talk. And hopefully in the next few decades, we may find out whether neutrinos are their own particle and what the neutrino mass really is. And NERSC will play a critical role in this endeavor. And I come to my acknowledgement. I want to thank Yunda Chan, Brian Fujikawa, and Brett Welliver, who provide some of the information of this talk. And I personally want to thank NERSC and the support staff for the sustained support of the program. I started off at the lab as a postdoc 26 years ago, and I've been using NERSC since then to do the analysis of my experiments. And here's one last thing, with a message from Art McDonald, who led the SNOW collaboration, and he won the Nobel Prize in 2015 for the SNOW work. And he wants to congratulate SNOW for 50 years of exceptional service to the community. NERSC was a very, very, very valuable part of data analysis for the SNOW project, which won the 2015 Nobel Prize and the 2016 Breakthrough Prize for the discovery of fundamental properties of neutrinos. And the storage of the data set in HPSS now have enabled further analysis of other physics topics, extending the scientific reach of SNOW. Okay, and so the final word is happy 50th anniversary, and I'll stop here.